Okay, last time we were discussing yesterday file system performance. We said that we know that the disks are very slow. Remember we had a picture long time ago about the memory. We said that registers are very fast, but they are very expensive, and the area of registers are very small. Then we have our main memory. Okay, these are the registers, and then we have the cache between the memory and the registers, and we have our main memory, and then we have our secondary storage such as disk and SSDs, and between these there is this cache. Okay, so usually if we have a difference in terms of speed and capacity, we put some kind of a cache memory between these two technologies. Okay, cache is between, in terms of size, it is in between registers and the main memory. In terms of speed, it is in between. So this way it is fast, this way it is large. Okay, that's the hierarchy. You remember this picture from our memory chapter. So when we are here, we know that the secondary storage is very, very slow, especially if it is mechanical. It is very, very slow. So what are we gonna do? Let's use some part of the main memory as a cache. So still the principle of locality valid for this case too. If I am going to access a block in a file, it is likely that I am going to access a close by block in the same file, or close by sector in the same same disk track. That's why we say that why don't we keep this kind of data in my cache? Okay, that's the idea of cache already, and we already have some good cache replacement algorithms, and LRU, we liked it a lot when we do the page replacement for our main memory. And this time we have an advantage because we can take a lot more time to decide which page to replace with the LRU algorithm, because we know that when we get the miss page, the cache miss, it's going to take a lot longer to get the data from the disk. So maybe why don't we take our time to calculate it right? So every time I make a reference to a disk block, okay, in my hash table, okay, in my hash table for the disk blocks, I can update the corresponding entry, and I can know which disk block I actually is least recently used and the most recently used, because I keep changing their positions. If I have used this one, if I have used this page, then this, not page but the block, I can put it at the beginning of the queue here. Okay, it's a double linked list, it's a queue, and I always replace the least recently used one. So I can update this data structure in a very efficient way. I can use it that way. So this hash table is like an associative cache, but it is in main memory. I don't need any special hardware for this. It's just regular hash table that you have learned in your data structures course. And if you need a block from a disk, you make a lookup in this hash table. If it is there, then use it. If it is not, then load it from the disk. But every time you make a reference to a block to your disk, you update its entry. You just say that, okay, I have used it, so I am going to make it most recently used. Okay, so that's not expensive, because that's, again, that happens when you try to load a block from the disk. So you can take some time to make data structure adjustments in this case. So we like this one. LRU works very well in this case, and we can't do much better than LRU, other than, I mean, if we could implement if I can implement the optimal algorithm, that would have been better, but it is not possible to implement. So LRU is the next best thing, but still we have some issues, as we talked yesterday. Okay, so I need to modify this LRU a little bit, because I know my application. Okay, my application is opening files, modifying files and directories, and etc. Depending on your file system type, some of the blocks are special blocks. For example, the inodes. Okay, in Unix, opening a file means that finding the inode and loading to the memory and keep it in your memory while the file is open. So it means what? I don't have to keep that block for the inode in my cache, because I have it already in my memory. So although it is maybe most recently used, I can say that I am not going to put this in the disk cache. That's one thing. The other thing is, some of the stuff that are very important, sometimes it needs to be written back to the disk immediately, like the inodes again. If I have modified my inode, maybe I shouldn't wait until I run out of cache space or anything like that. I should write it back to the disk, so that I have a better chance of keeping the system stability. Okay, so these kind of small modifications to the LRU, we should be fine. Okay, so why are we talking about this now? I mean, I did not remember, we did not talk about the system cache between the registers and the main memory in this course, because that is almost always handled by the hardware. Hardware handles it. It has to be fast, so hardware handles it. So it is not within the scope of this course. We are talking about operating system, not system architecture. Okay. So in your architecture courses, they told you about the caches. We are talking about the cache here. Okay. We are talking about the cache here between the main memory and the secondary storage. It is because it is handled by the operating system. That's why we talk about it. Or we talked about the page placement algorithms, because it is mostly done by the operating system. That's why. And some of these stuff we talk about, some of them we don't. Okay, so we talked about it, and then maybe this one. Okay, so some systems, for example, Windows says that I will be on the safe side. Okay, I will never keep any cache entry, any dirty cache entry. Okay, all the cache entries that I am keeping in my cache are referenced, but they are not modified. As soon as a cache entry is modified, I write it to the disk. Okay, I don't make them wait. These are called write-through caches. Okay, write-through caches, you never wait until your dirty cache entries needs to be written to the disk. You just immediately write them to the disk. So what does that mean? If a system crash occurs, you are safe. Why? Because you wrote everything back to the disk. You don't keep an unmodified version of your data in your cache, so you are safe. So that's the advantage. What is the disadvantage? What is the disadvantage of having write-through caches?
It should access the disk, so it takes some time.
Yeah, because if I keep writing to the same disk block, instead of writing it to the cache in a very, very fast way, I keep writing it to the disk in a slow way. So it has some performance issues. Okay, I can't use my cache to make it faster. Okay, that's the disadvantage. The Unix uses the other way. Unix says that, okay, I am a stable operating system. I don't crash that often. Okay, so I am going to keep all the modified cache entries blocks and all the reference blocks in my cache until I am running out of space, cache space. So that's the problem. That's why if you are writing to a USB disk on Unix, okay, and if you take your USB disk out without dismounting it, you will lose, most of the time you will lose whatever you have written to the USB disk, because it is not written to the USB disk yet. Okay, so you need to dismount it first, and when you dismount a USB disk, Unix puts all the modified blocks to the disk, and you will be safe. I think Windows has changed this maybe 2 years ago or something. By default, I think it is the Windows 11. I think it is doing this. I think it is doing the right through stuff. So maybe it is doing it for the SSDs, but not for the USBs. I don't remember the detail exactly, but for both systems, this is adjustable. You can say your operating system that I don't want write-through caches. I always need write-through caches and etc. Okay, so it's a system parameter. So it's a good thing to know about your operating system. Okay, still we are talking about the cache stuff. Okay, read ahead is a technique that is used for the cache. Usually when you read a file, you just don't read a block from the file, just not just a block from the file. Okay, when the file system asks you to produce the block K in a file, give me the block K in the file. Okay, your file system intelligently, in a smart way, okay, it gives you the block number K. When it is finished, okay, it makes another schedule to bring block number K plus 1. Okay, so it kind of guesses that, well, whoever needs block K, it needs block K number 1, and it works very well for the sequential file reads. If your file system is smart enough, maybe by looking at your previous history of reading the blocks, maybe it will know what you're going to need next, and etc. This is called read ahead. Okay, this is called read ahead. Of course, it has to be optimized. If there are other requests for reading the blocks from your process, those other requests should get the priority. If your disk is idle, why don't you just read the block number K plus 1? Because my disk is idle anyway. I'm not going to lose any time. There are no other disk requests and etc. Okay, so these are some tricks that you can play with to increase your file system performance along with the caches. The other thing is that if you know what kind of technology you use in your secondary storage, whether it is mechanical disk or SSD, you can take advantage of it. Okay, and since we are using the mechanical disks a lot, maybe we can do some optimization about this disk structure to reduce the disk arm motion. Remember the disk arms? Okay, remember disk arms? Disk arm is something like okay, this is the pivot point, and it can, by just rotating this this way, I can either read this part or read that part. Okay, so this is the disk arm motion. I know that I am going to need to move this disk arm that way, either clockwise or counterclockwise. So, and I know that my disk head has to be somewhere on my desk. Okay, on the average, I would say that this part of the desk is on the average most easily accessed, because you should be close by to the center track, center cylinder. Okay, so some people say that why don't we, okay, why don't we keep our most important and most frequently used disk blocks, that are the inodes, in the middle of the disk, in the center cylinder. Okay, that way, whenever I open a file, okay, whenever I modify them, I can immediately go to the center cylinder and do whatever I want. Of course, you will need to spend this disk seek time, average seek time. That's what we are going to do. But average better than longer times. That's what some people say, or some other people say that, okay, why don't we apply the same idea like this? I am going to partition my disk into areas like this. Okay, this is area number 1. Okay, these 2 tracks, and the area number 2 is this. Area number 2 is this. Okay, the concentric ring just after that, and the area number 3 is, for example, this one. You know the idea. So I keep my files either in area number 1, area number 2, area number 3, and the related files are kept in, for example, in this blue area or the green area or the red area. So if I keep my inodes of the red area in this part only, so whenever I am reading those files, okay, red area files, I know that my inodes and related files will be very, very close by in terms of seek times. Rotational latency, it will come, you cannot avoid it. But the seek times, I know that I am either on this track or this track if I am dealing with the red files. For example, red files are my user files. I have many other users in my system. So if I keep the files and the inodes of those for each user in these kind of cylinder groups, it's called cylinder group. Okay, so I may end up using shorter disk access times. Okay, shorter seek times. Okay, that's one optimization people use for the disks. Okay. You might say that, well, these are all for the mechanical disk. How about the SSDs? SSDs have this the interesting property. I mean, at least the first and second generation of SSD technologies used to have this. Nowadays, they are doing better in terms of this problem. If you keep writing, well, in SSD there is no mechanical part. Okay, this is a solid state storage unit. Okay, it is the same speed wherever you read. Okay, if you read from the beginning of the SSD or end of the SSD, middle of the SSD, it's the same speed, doesn't matter. But the technology says that if you keep writing and reading from the same area of the SSD, that will wear out. Okay, that block will get damaged, and you won't be able to use that area much. So it will be a bad block, bad sector, if you like to call it that way. So it is the task of either the hardware or the operating system to keep changing the use blocks of files from time to time. So you keep moving your files around on these kind of SSDs. So this is not a performance issue in terms of access performance, but it's a performance issue in terms of longevity of your SSD devices. Okay, as I said before, newer SSD drives, they don't have this problem much, but some of the cheaper ones may have it. Okay, so doing these kind of tricks, depending on your device type, is always a solution. Okay, and when we come to the I/O chapter, we will talk about the secondary storage units a lot more. This chapter is about the files, not about the hardware. Okay, so why are we talking about the hardware now? Because we are talking about the hardware to make our file systems faster running on that hardware. That's why I switched to talking hardware. But when we come to the I/O chapter, we are going to talk more about the hardware. It's not because it's not because we like to know the hardware how it works. It is because we like to be able to write a more efficient, more compact, more reliable operating system device drivers for that kind of hardware. Okay, so that this reducing the disk arm motion is something that we always try to achieve. Good. Any questions? So let's look at two example file systems that are currently in use. One of them is the simple one, MS-DOS file system, which uses the file access table approach. This is a simple structure of the Microsoft disk operating system file system directory entry. When you have a directory, in your directory you have entries fixed size. Okay, this is fixed size. How many bytes is this? It is this is 12, 22 and 28, 32. Yeah, 32 bytes. 32 bytes for each MS-DOS directory entry. It is fixed. You cannot make it smaller, you cannot make it larger. It is 32. Since it is fixed, it is very easy to access the fifth element of a directory entry and etc. We know those. And that's an advantage. The disadvantage is what? What is the disadvantage of having fixed directory entry? Yeah.
It limits file name or extension, or while if, for example, Microsoft wants to add something.
It would be difficult to add more information later, you are saying? Well, that's why they have this 10 bytes of reserved space, but what if I want more than 10 bytes? Yeah, that's the thing. The other thing is your file names has to be 8 bytes. No smaller, no larger. It's 8 bytes. Okay? Remember that problem. Your extension has to be 3 bytes. Those are the problems. But again, this is a file system designed for microcomputers of the 80s, 1980s, and you had to take a trade-off between having a very flexible file system or having an efficient file system. So they choose the efficient one because the file systems those days, or the disk drives for those systems, were very, very expensive for the home use. So you need to make best use of them. Okay, that was the so file name 8 bytes, 8 characters, extension 3 characters. These are the attributes for just 1 byte. So what does that mean for the attributes? It is like 8 bits. For example, a read-only bit. Okay, it could be a bit. The hidden file is another bit. System file is another bit. What else the MS-DOS can do with the files? Maybe executable is another bit. I don't remember that one. So those are the attributes, and these are reserved for operating system use. They don't document what they are used for. Usually they are used for different versions of the operating system. For example, in the next release of this file system, Microsoft decided that I am going to support Unix-like ownership. For example, the owner group and the others. Maybe I can use this area to keep that information. This is the date and time, and this is the first block number. Okay, so remember this file system is FAT based, file access table based. What is file access table? It is a linked list structure that you keep in your main memory. Okay, you go to it. It gives you the next block for your file. So you get your first block. It says that your first block is. Why did I do this? Okay, this is a table, right? So you get your first block. Your first block is here, and then you get the first block number. It is this one, and from that you get the second block number, and then you get the third block number, and the third block number says that I am done. There is no next block. So it's the linked list. Actually, we have seen this. I always keep this in my memory, main memory. That's why you don't want this to be very large. If it is large, then you will run out of your main memory. You will run out of your main memory. We talked about this. Yeah, this is the first block, and this is the size. I guess size in terms of blocks. It is no size in terms of maybe blocks. Maybe because it is two. This is 4 bytes. That means 32 bits, right? Is 2 to the 32? Yeah, it is 2 to the 32 blocks must be. Yeah, because 2 to the 32 bytes is small even for this kind of primitive file system. Okay, and depending on the block size, again, we have different versions of the file access table file systems. FAT12 means that I am using 12 bits to address the blocks. Okay, so this table, this table has a size of 2 to the 12. Okay, so 1 kilobyte to 4 kilo entries in this one. Okay, 4 kilo entries, 2 to the 12. And then FAT16 is uses 16 bits, and this is 32 bits. If your block size is half a kilobyte, that means that if your block size is 2 to the 9, right? Half a kilobyte is 2 to the 9, and you have 12 bits for the block. That means that 12 plus 9 is 21. 2 to the 21 is 2 megabyte entries. Yes. Okay. So half block size FAT12 can give you at most 2 megabytes of disk space. Okay. And if you are using FAT16 and 32 kilobytes of block sizes, then you can get 2 gigabytes of disk space and etc. You know that. Okay, as you see, it looks like, I mean, you can change what kind of FAT size you can have on your desk, and you can choose your block sizes. Later they remove this half kilobyte and 1 kilobyte block sizes for 16 and 32, and still we are using this FAT16 and FAT32 a lot nowadays, because Microsoft says that I am not going to ask you to pay licensing fees if you are going to use this, and that's nice, that's good. Well, I mean, these file systems are not very difficult to implement, so I can implement them, that's fine. But I can design some other very simple file systems like those, and I can use them. But the nice thing is that these are known, these are standards, right? I mean, people have been using these kind of file systems for the last 40 years, so there have been lots of devices formatted this way using this file system. Why don't I use it for my very new device to support especially removable media? Okay, especially the removable media such as small memory cards and etc. So these are very popular, as I said before. Good. So this is one case of the file systems. The other one is Unix system 7 v7 file system. Okay, so the directory entry for a Unix file system is like this. It is just, it looks funny. File name 14 bytes. Well, it looks like the file name is fixed for v7, but we didn't show you the whole picture. And then I have the inode number. We don't have anything like our attributes, our time, date, size, and etc., and the user information, etc. This is so simple. Why is it so simple? Don't we keep those kind of attributes, metadata about our files in Unix? Why is this so simple?
maybe
So,
it keeps
what is your name?
Yunus Emre.
Yunus Emre, where have you been? You started talking for the last 2 weeks. You are not coming to the wrong class, right? Yeah, this is operating system.
No, I think I.
You have been coming to the class for the beginning.
Oh, yes.
Okay, good. So sometimes I teach wrong
I like
stuff to
the
wrong
topics,
people, so I don't.
actually,
Okay, so why is it so?
I think maybe it's stored in the file itself. Not.
We don't keep our metadata in the file because file keeps information about the information that we like to keep. But you are close. We keep data in the inode. Inodes are special blocks, remember? So when we say I have an inode number, remember inodes are kept at special places in our disk partitions. Inode keeps block addresses, right? That's why they are called inodes. When I open a file, okay, I find the inode for that file and I load it to my memory, and this is the inode. Inside the inode I have the attributes. Okay? Inside the inode I have the attributes, and after the attributes I have the block addresses. And I am free to keep any data that I like in my attributes field, including the long file names, modification time, creation time, reference time, and etc. Okay, this is system V7, and this one uses 1, 2, 3 level of inode indexing hierarchy. So the first elements of this inode addresses directly the blocks. Let's say I have a 4 kilobytes of block size for this inode. In my 4 kilobytes, let's say I use 1 kilobyte. This is just an exaggeration, but I use 1 kilobyte for the attributes. I have 3 kilobytes for these indexes. Let's say each index is 32 bits. Okay, so 4 bytes. I am going to do this 3 to the 10 over 2 to the 4, right? 2 to the 5, yeah, 2 to the 5. So it's going to be 3 times 2 to the 5 entries inside this attribute. But so it is 3 times 2 to the 5 entries. Each one is 4 kilobytes, so it is 4 2 to the 10. It's going to be 12 2 to the 15. Okay, so well, it's not going to be very large. We are talking about a file size of on the order of a megabyte or something. That's very small, but I didn't finish yet. Okay, I have special indexes at the end of this inode table. This one points to another inode, okay, and that inode has indexes in it, so I can have many more blocks. This one is even more special. It has a double index block. This one has indexes to another inode, and these inodes have indexes to the real blocks. And the third one is the most special one, triple index block. This one is an inode, this one is an inode, and this one is an inode. Then I have the real blocks. Okay. So if you do the calculations, I can address gigabytes of file spaces that way. Okay. So it is simple, but it can do anything that you like. And if you like to keep very small files, then it's okay. You don't use this single indirect block or the double or the triple indirect block. It's very simple. But if you like to keep gigabytes of data in your file, then this one is okay with that too. Okay. Again, invented 1960s, 70s maybe. Very simple structure. It can do whatever you want with your file system. Okay, our newer file systems, NTFS or the resilient file system or the exe34, etc., they are using these kind of ideas. Unix always used this idea of inodes, And NTIFS has a hybrid kind of an approach that uses the FAT system and the inodes. We don't do, I mean, these kind of things are already known. I mean, people have studied these kind of systems for the 1970s and 90s and etc. Somebody was asking me about the question. I mean, whatever we have looked at, they are all invented in 1970s and 80s, right? So what did we do in terms of operating system development in 2000s and 2010s? Well, I mean, there is always something to work on. System performance, okay, multi-processing, trying to make systems more robust against failures, okay. I think I talked about this. Our operating systems are very robust, even knowingly, if you crash some part of your operating system, they will not go down, okay. They have ways of repairing themselves. Even if you have a electronic failure, CPU, remember the bit flop problem with the electronic devices. Even if you have many bit flop problems with your system, your operating system will keep running. Nowadays, we have that kind of stuff, and almost everybody with these kind of devices, we use these operating systems at mobile platforms, so battery management and etc. Those are important stuff. But the thing is, right? We have been using the same structure, same operating system structure for the last maybe 30 years. Virtualization is used a lot, okay? Sometimes you would think that you are running that operating system, but underneath you are running some other operating system and nobody knows about it, other than Microsoft, for example, other than Apple, okay? Apple especially is very secretive about their operating systems. For example, our book doesn't have a chapter about Apple operating systems. It has a chapter about Unix, Microsoft, and Android, but not on Apple because they are not documented publicly, okay? So who knows whatever they are doing, okay? They don't make a promise. So it seems that way, but underneath there is a virtualization happening and maybe some other stuff is running. Good. So I think we looked at this picture before, okay? If this is the case for a directory entry in Unix v7, maybe this is a sample example directory listing. I have these directories, bin and devices and libraries, etc. Okay, these are the inodes for the corresponding stuff. So the inode 6 is this one, user. So the user says that user says that, okay, my access mode is this, my size is this, the access times are this, and I am a directory, and you are going to find my directory listing at node number, block number 132. If you go to 132, you have another directory, and inside the directory you have the same stuff. Remember this? That means, okay, this is my directory, this is myself, and my inode number is 6. So it points to that one. Also this one points to that one. Okay? And my parent directory is the root. It is this one. This one also says that I am this. Okay? So these two are again special. And by the way, this is the only directory that can do this. My parent and myself are the same thing. Okay? Other than the root directories, you don't see anything like that. Good. Let's look at a third file system. This is a standard ISO standard file system, 9660. It's a CD-ROM file system. Remember, we like I mean, why are we looking at the CD-ROM file system? Because they are simple to look at, and they are kind of special. Why? CD-ROM means that you write your files once and you never modify them or remove them. Okay, that's why contiguous allocation is very nice alternative for these kind of file systems, and they do it that way. Okay, and by the way, in CD-ROMs, our disks are concentric rings like this. Okay, these are our tracks for our disks. CD-ROMs are not like that. They have their tracks, and their tracks are like spirals like this. Okay, so once you touch to one of your tracks, you keep following it. Okay, you keep following it, and there is no track number 7, track number 5, or there is a single track, and that's it. You start reading from this end, and you read until you reach at the center part continuously. Why? Because CD-ROMs are actually developed for what? At the beginning they are for audio. Exactly, for audio. Okay, for sound. Okay, they don't have a concentric cylinders. They have a single continuous spiral containing the bits. Okay, and usually you don't. I mean, remember on disk we have an addressing method of sector number 7 of the track number such and such. In CD-ROMs we don't use that kind of addressing. We just say that, okay, one CD-ROM can, let's say it holds 100 minutes of sound. Okay, you say that I need to go to the minute number 72. Okay, minute number 72, second number such and such. So you address your position on a CD-ROM by the minutes and the seconds, because they are designed this way. Well, I mean, in the data world, we don't talk about minutes and seconds, so it is easy to convert between them, because 1 second of data corresponds to 75 blocks, if you like it that way. So if this is 1 second, there are 75 blocks inside 1 second. Okay, they work just that way. Okay, so the International Standards Organization, ISO, okay, came together and they decided that let's make this a universal standard, international standard. Whoever is going to keep data on the CD-ROM, okay, should follow these rules so that we can have compatible music players, compatible video players, compatible data recorders and data readers. Okay, that was the idea, because when they have invented these CD-ROMs, there was a competition between many companies, and it was the issue, it was a concern. What if we are using the same technology, but we are not compatible in terms of file systems? So this is the file system that everybody should follow. Okay, this is the directory entry for a CD-ROM file system. Okay, it is not fixed length. Its length can vary. Okay, so this is directory length entry. So say that 1 byte. That means what? I can be between this and this. Okay, I can use 1 byte for that one. This is extended attribute record length. If 256 bytes of directory length is not enough, then you can have an extended attribute length of 256 bytes again. This is the location of the file, 8 bytes. That means what? My file is at this minute and second position on the CD-ROM, and this is the size of the file. This is the date and time of the creation, not modification. Remember, I don't keep that information because I don't modify it, or not reference. Okay, I don't keep the reference time, the last reference time of my CD-ROM file, because I cannot modify it. CD-ROMs, once you write it, you don't modify them. Then we have our flags, such as I can say read only, write stuff. Okay, other stuff like the hidden file, maybe empty parts and that kind of stuff. I don't know what kind of flags they have. Internally, we are going to talk about internally when we talk about the desks. CD number is, for some libraries, one CD is not enough. Let's say I have 10 CDs for that library, okay? And this one says that you are going to find this file in Cd-Rom number 5 and etc. And then after that, I have my file name. It is between 4 to 15 characters. It looks like it is limited by 15 characters, but as I said before, there is an extended attribute length, so you can put more information at the end of this directory entry by specifying that I have that much more information after this. Okay, so this is a little bit more complicated than MS-DOS directory entry. It doesn't look as simple as the Unix inode structure, but directly from this you go to your file, okay, by following this location of the file. Okay, good. So when you look at this one, you might say that what happens if I use this CD-ROM on my Unix file system? In my Unix file system, I need to store information about the user information. Who is the owner, right? Who are the group owners? And what are the permissions for the groups and the others and the users, right? I need that information too. How am I gonna put these? So they came up with this Rock Ridge extensions. Okay, so these Rock Ridge extensions, they have added these attributes, okay, which are normally found on POSIX systems, to the extension part of the CD-ROM directory entries. Now, if your CD-ROM is if it supports the Rock Ridge extensions, then it can behave like a Unix file system. So I can, let's say, if this is my root directory and this is my user directory, if this is my devices directory, under mount directory you can mount your CD-ROM, and under CD-ROM you are going to see your files like regular Unix files, because that CD-ROM supports this kind of stuff now. I have my POSIX attributes, device numbers, parent location, child location, etc., timestamps, and etc. Okay. Later they say that if we are doing this, how about more extensions, Jolite extensions? Okay. With this one again, it's an ISO compatible, longer file names, Unicode character set. Well, I mean, in MS-DOS file systems and the original Unix file system, you cannot use characters other than the ASCII characters. So if you like to use letters like Turkish characters like these letters, you are in trouble. And usually, if you remember, some time ago we tried to avoid using these kind of characters from for our file names. Nowadays we are not careful about those. So the Unicode character set is supported by only this extension for the CD-ROMs. Okay, and directory nesting deeper than 8 levels. I mean, if you like to have a directory under another directory, the original one can go at most 8 levels. If you like to go deeper than 8 levels, then you need this extension. And again, directory names with extensions. You have a directory name, but I like to have an extension to it, then you need to use this Jolite extension. Okay, good. Any questions about the chapter number 4, files and file systems? That was the third main leg of the operating systems. As we said before many times, these three concepts, processes, address spaces, memory address spaces, and the files, are the three main concepts of the operating systems. If you know them, if you know how to remember the two purposes of the operating system: abstracting away the details of the underlying hardware Okay, abstract away the details of the CPUs, threads, multiprocessing under the name of the process. Abstract away the details of the memory, multi-user memory, multitasking memory, those MMU stuff and the replacements and etc. Address spaces, and abstract the details of the, as you see, the file systems are much more complicated than the other stuff. If you know these and if you know what's going on with these, then as the book says, you are becoming a operating system. What did the book say? Yeah. If you really understand these three concepts from the beginning to end, you are well on your way to becoming an operating system expert. I am not saying that you are an operating system expert, but you are making good progress. So I think I will stop here. Let's take some break. After the break, I will continue with the next chapter, which is about input-output. Okay. So let's be here around 15 minutes of break. 11:43, 44. What? 39. Ya. Onu versene bana. Ha?
Ben bir 10 dakika geç kaldım. Şuraya oturdum.
Tamam, 10 dakika geç kalmayın. Ya ben burada yokluğum ayamayım. Onu bir yukarı çeksene ya. Sen ne yaptın? Soğuklarda üşüdün konuşamadan havasıyla mı konuşmaya? Niye konuşmaya başladın? Ön tarafa mı oturuyorsun? Neyse konuş da ne yapıyorsun? Seni şeyle ilgilendiriyor diye. Hocam yapıldı dinliyoruz dediniz ama.
Çıkamadım işin içinden. Bir de kendi mantıklarını yazmışlar.
Sıkıntı yok.
Arada çıktı ders.
Ben gidiyorum.
Dans hep derste geliyor mu?
O zaman yönetimi.
Kanka başladı.
Ama daha bu arada buldum YouTube'dan.
Arada çıktı.
Çok güzel.
Arada çıktı de.
Ben bir kere de
Benim adım söyle.
hatta bir şeyler de söyledim.
Benim adım sorar. Söylerse.
Bizimkiler izliyor ama şu an şey var. Çok anlatıyor. Bir şey anlatıyor yani. Basic bir şey adım adım. Evet, anlatıyorlar. Güzel ama böyle kanıtsamam. Şunu yap, şunu yap. Buraya bağlı, küçük bir şey. benim işte geçen
Sana daha mantıklı gelmiyor mu?
Bak
Zaten
hocam bak
mesela
dur.
bana yaptığım şey
alıyorsun ki
evde şey
mikrofonu.
ilk ödevim.
Puan değiliz.
Kalıyorsun ondan doğru şeye
Ben sınırdayım zaten.
vereceği oradan
Sınırda
da
mısın?
topa davranan bir şey var.
Sen bayağı girdin dedin de o yüzden şey sandım.
İkincisini verdim.
Ama eksiğim var.
İkincisi böyle işte bir ekran
Yani
var. Bir arada
burada
bir
ismini okur.
Geçenler burada bir
dediğim raporlardan yapılmış.
Belki. Peki arada
Geçenler
sen bırakmasın.
Ama şey, Ruh'da geliyor ya mesela eski işler çıkarken ondan ya o çok güzel. İşte leverajın hükümde leverajın işte ekranlar arası olacak. Tekniklerle geçiyor falan filan. Tetiklemeler var ya. Ama daha çok onları kullanacağım diye.
Bizim şirket biraz küçük olduğu için şey böyle çok ödev değil de bak müşteriden bu iş geldi hadi sen yaptın çakıyor müşteri işini sana atıyor. Oluyorsun ama küçük şirket öyle oluyor. Çünkü çok işi var yapacak adam çok olmuyor.
Ya bizim işte 2020'si benim benden 2 yıllık o zaten bacım. O şey yapıyor. Çok yeni gelen var. Yani her ekip yeni bir kişi alıyor diyebiliriz. Ben girdim üst böyle büyük şeylere giriyorum zaten. Söylediler. Şimdi bizde en çok oraya gidiyorlar da bir içinde. Mesela ablaları test yapmışlar. Benim ablamın eski çalıştığı şey zaten. Benim ekip ve o tarafa
Bizim şeyimiz yok. Ona yani normal default şeyimiz neyse ona göre tanımlan. Sahaya gidildiğinde o şekilde bir bağlantı yapılacak.
Tamam. Hani yapacağım şey.
Ama en azından bir şey soruyorsun, yardım ediyorsun. Ben artık alamıyorum da kimse. Herkes çok
Yok, bir de herkes
çok kötü ya.
Bahte sorma sorma. Şey çıktıktan sonra soru soramıyorsun.
Evet, çünkü acemileri hep cevap veriyorlar. Sen bu şekilde yolunu bulmak zorundasın.
Ben ne yapıyorum? Şimdi mesela ödevde mesela en basit şeyleri çok bilmiyorum ya, tabloları. Şey var ya mesela işte miktar ölçümlerine tabloyu tekrar başka tabloya vermem gerekiyor ya. Tabloyu falan. Tablo ölçümleri daha hakim değilim ya. Ne yapıyorum?
Ama onu sana modülcü söyleyecek, sen onu
Ama ben şimdi
uğraşmayacaksın.
ödevlerde kendim yapıyorum ya. Hatırlayamıyorum ya daha hatırlayamıyorum. Ablama hemen ısıttım. Abla diyorum.
Çok güzel.
Abla diyorum bunu hangi tablodan çekebilirim? Hemen yazıyorum. Ya da bir şey yapacağım. Hani anlatıyorum nasıl yapsam şu fonksiyonla yaparsam. Çok şükür bir
Nişanlı modülcü olduğu için abak konusunda soramıyorum ya. Yine de normal
Paşa ne yapıyorsun?
zaman yönetmeninde. Bu da yurt dışına çalışıyor zaten şu an projeden.
onların
İyi ya Allah kolaylık versin. Şimdi bu gece 10 MHz levelleri için template atıldı. 2 tane sahada şey yapılamadı, atılamadı vakit yetmediği için de. Şimdi o template hazırlıyorlar ama onu bir gece atacağız. Ama ekipler ve çok o saha ziyaretlerini yapacaklar. Biber çekecekler de. Onlara sen o 2 saha için en azından destek olabilir misin? Doğru yere taksınlar en azından.
Ya geçen de onu sorduğum galiba bir yurt dışı.
Yok gece atıldı. Gece atıldı template'ler.
Konuşabiliyorsan konuşmadım.
Yok işte ben.
İşte onu diyeceğim. Yani onu şey yapacaklar. Değiştirecekler. Sahaya gittiklerinde. Yani sen diyorum destek olsam en azından doğru yere taksınlar. Ha öyle mi? Evet tamam.
Allah kalamıyor ya.
Tamam. O. Tamam canım. Onun için aradım seni. Güzel, tamam. Tamam. Onun için aradım.
Takasam sen de değil mi?
Tamam.
Yazar
Onun için dedim ben.
Her ne kadar alanlarımız çok şey olmasa
Tamam,
da
hadi görüşürüz.
şey fonksiyonlar, abak
Ya öyle hatalar oluyor ki mesela benim şey video atıyorum. Vallahi bir defa böyle bir hep bana dönüşüyor.
Bence yok, sen güzel kurcalıyorsun. O yüzden o hatalar çıkıyor. Garip bir
Vallahi baktım bu ilk defa böyle bir şey görüyorum. 2-3 kere böyle oluyor. Hani hep yeni bir şey çıkıyor.
olur vallahi yaz. Ben de şey yapmadım.
Ya herhalde yapmaz diye düşünüyorum.
İnşallah.
Diğerleri oluşmuyor. Bir soru. Üç tane thread oluşturdum, iki konsümün bir supply oluşturdum. Bak, dedim ki i eşittir 1 ise ve 1 ise beklet dedim. Bir saniye. Bak direkt. İki başladı. Sonra 1 geldi. Bak mesela ben bekletmedim. O ara interrupt oldu. Ben 1 ise ve 1 ise beklettim. 2, 2, 1, 2, 1, 1 çalışıyor. Bir de böyle çağırdı. Join yapmadım aslında hiç. Join'i deneyeyim. Join'i çalışmaz. Nasıl bitiyor bu peki? Gelsin mi? Bunu yapınca olmuyor güzel. Böyle güzel çalışıyor. Yok skill'de değil. Ne demek? Yani anlamadım bir şey. Bakalım nerede? Üç tane ama 3 tane sonra 1, 2, burada böyle çalışıyor. Böyle çalışmaz. İşçi mi oluşturdun? Nerede gördün ki oğlum? Ben internete baktım, bir saate bakıyorum. Genelde aynen böyle bir
Önce ben.
Okay. Chapter number 5, input output. We looked at my pen. Okay, we looked at these 4 chapters. Introduction, you remember introduction, actually in your introduction chapter kind of told you everything about this book, about this course, kind of an overview. we talked about the processes, memory, file, I/O, even I/O, and then we looked at these three important chapters. Now we are going to look at this I/O chapter, and after that, maybe while I'm looking at it, let me go to. Okay, maybe look at the book. Book is here, right? Okay, book is yeah. This is the book. Let's look at the contents of it. Yeah, where are the contents of it? Okay, chapter number 1, chapter 2, 3, we are going to look at the chapter number 5, input output. Then we have this deadlocks, and I am not going to talk much about the deadlocks, maybe a little bit introduction, that's it. I like to talk about this virtualization and cloud. That's one thing that I like to do. Maybe some security and some multiple processor stuff. And after that, it is the just case study for Linux, Unix, and Android. Okay, we have been looking at this stuff from time to time. Windows-based stuff, Windows 8. I mean, it is more involved in there. And then some design issues, but these are kind of graduate level studies. And that's it. That's the whole operating system book. So that's my plan. Just a little bit after that, just a little bit deadlocks, mostly virtualization and security. That's my plan. And I suggest you read this case study stuff, Unix, Linux, and Android, and Windows. So how the things are done with these operating systems. For example, you just click on this, okay, processes and threads and etc. Let's see in Windows, where is security, window, input, output, caching, memory, where are the file systems? So since the file systems are not specific to operating system, because I can use the NTFS file system anywhere I like, I think they did not talk about it. Yeah, they did not talk about it that much. Maybe they talked about it in the. No, it is not there. I just wanted to go there and show you some NTFS based stuff on there, but it's not there. Anyway, so let's go back. By the way, there are other books. Read those other books too. I think I have copies of those and you can find them too. Operating system concepts. This dinosaur book. Okay. Where are my dinosaurs? Okay. So these are the chapter structure. Introduction is the same. And operating system structures is the organization of operating system. And this chapter is more fine-grained in terms of chapter distribution to the ideas. Okay. The processes, threads, and CPU scheduling, process synchronization, and deadlocks are kind of early in this book. So these four stuff correspond to our chapter number 2. Then the memory management, virtual memory. Okay, that's our chapter number 3. Then the file system implementation, mass storage, and then I/O. Then protection, security, and etc. You see. I mean, the structures are always the same. They always will keep talking about abstraction and the management of the resources and etc. Maybe this book is more detailed than our book. Okay, maybe this is a more reference type book than our book. Our book is better in terms of. I mean, for educational purposes, I think it is better organized, better. Sentences are better. The author is a more fun guy, although he's old. Maybe he's dead. I don't know. This dinosaur book, the operating system. Yeah.
Which one are you?
Silby shots.
Are you teaching this one or the other one?
This is not our book. Our book is Tannenbaum. Yeah. So I am telling that what kind of other resources we have. that they can. Okay, I'm giving him some reading material for the summer. Okay, let's go back to our input output chapter number 5. So IO is okay, is an important part of the operating systems. Although the idea is simple, I mean the whole thing is about this stuff. Okay, we issue commands to the devices. You know, you remember what the devices are, right? And the devices, when they complete whatever they are issued, they produce interrupts that cause interrupts. We catch the interrupts and we handle the interrupts, and the errors occur, we handle the errors. That's the whole thing. But since we have so many input-output devices, so many types, I mean, when you say keyboard, there is not a single type of keyboard. When you say secondary storage unit, there is no simple secondary storage unit. There are so many of them, okay? Since there are so many of them, and they are complicated devices, electronic devices, somebody has to handle them. So we need to write code for those device drivers. That's why I/O code represents a significant fraction of the total operating system. Okay, I mean, if you think about our scheduling algorithms, well, we talked about them a lot. If you think about memory management algorithms, page replacement algorithms, they are mostly simple algorithms. They have to be, because they have to run very fast. You cannot write millions of lines of code for process management and etc. But for the I/O, it is different. Literally, you need to write millions of lines of code for the I/O. And what did you say? Windows 8 or Windows 10 has 80 million lines of code. Nowadays, we are hitting like 100 million lines of code for an operating system. Most of that code comes from the I/O part. Okay, I/O idea is simple, but it is complicated because there are so many details of it. Remember our simple picture here. We have CPU and MMU and the memory. These are the controllers, and the controllers are connected to the actual devices. Okay, we just say that this is an electronic device which helps us communicate with this hard drive itself. In real life, this hard disk controller, along with the hard disk, is another computer with its own operating system. Okay, this is a computer with its own operating system. Mostly they are running Linux. Okay, and they have multi-processors on them sometimes, more than one processor.
You don't have any networking stuff here? Networks is not I/O?
Well, see, this bus is continuing. I don't know. Maybe they have it. I mean, this is just a concept. Okay, this is a more realistic picture. If you need more information, go to Wikipedia. So this is complicated. I need to communicate with such a complicated environment. You might say that, well, if this is complicated, this will make our job as an operating system designer or expert easier. That's kind of true and false. Why? Because there are security issues. For example, I know there are some viruses. They install themselves on this hard disk computers. Okay, and they do their stuff in there, and then you have an infected hard disk controller. It is doing both the hard disk service, and it is doing some other bad stuff. Maybe zero day traps. You know those 0 day traps that they wait until January 1st of something, and they immediately start pinging the FBI headquarters in USA and putting their computers down there, etc. So the main idea is, yeah, I/O is simple, but there are many details, and we are going to look at them. Okay, and as the operating system, what is one of the main tasks? Hiding away the details of the hardware, abstracting away the details of the hardware, and managing all these resources. So operating systems are involved a lot in the processing of the I/O. Okay, doesn't matter what kind of hard drive, SSD, or any other kind of storage I have, network storage. As an end user, as a system programmer, I say that open file and I don't care about the rest, right? I don't care if it is a CD-ROM file, a DVD file, network file, SSD file. I just say open it. Who handles the rest? Operating system with the help of the I/O drivers. And for most of the operating systems, as you know, I/O drivers are the part of the operating system, the kernel part of the operating system. Okay, so the book is structured this way. It's going to talk about three. So he got bored. Okay, so he knows how you feel now. So there are three main titles. Okay, we will first talk about the hardware. This course is not about hardware. Okay, it is about operating systems, but we need to know just enough hardware so that we can talk about the operating system part of it. So we are going to look at the hardware first, then the principles of I/O software, what kind of issues we have about them, and then we are going to look at the individual I/O devices one by one. For example, we are going to spend lots of time about the hard disks. We are going to spend lots of time about timers. Remember timers? Although timers are very simple, again, I keep saying simple. They are simple, but they are so critical in our operating systems because they are responsible for causing the interrupts, timer interrupts. Without the timer interrupts, no multi-user time sharing systems could be possible, maybe. Also, remember when you go to sleep, somebody needs to wake you up from time to time, and etc. Those kind of stuff, timers are important. For example, one of the I/O devices is a timer. You might say that timer is not exactly an I/O device. It doesn't give you any numbers back. You don't put any numbers to the timer. Yeah, that's true, but it's a device, and it is connected to the system bus, and we call it an I/O device, or maybe more correctly, device. Okay, so we are going to look at them one by one. And for example, we are going to look at the keyboards and the display drivers, and etc. Although not much time I am going to spend on them. Okay, so let's go to these principles of I/O hardware, and let's look at the types of the devices. We usually like to divide these devices into two: block devices and the character devices. Block devices are, as the name implies, the devices that we access by the units of blocks. Hard disks, for example, or any secondary storage, most of the secondary storage, they keep their information in fixed size blocks. Okay, you say that your block size is 4 kilobytes, yes. When you say give me like 2 bytes at this address, it gives you one block, because the block is the minimum number of minimal unit of the transfer between your computer system and I/O device. Okay, transfer are in units of entire blocks. Remember our graph about block size versus the disk utilization versus the throughput rate. Okay, data transmission rate. That was about the critical decision of the block size. Which block size performs better in terms of disk utilization or the disk transmission rate, and etc. So that's the block size what I'm talking about. The other end is the character devices. Character devices are not addressable, actually. You either say get that value or give me that value. Okay, keyboard is a character device. It gives you some characters one by one. Okay, delivers or accepts streams of characters without regard to block structure. You can't say give me the characters, give me the character after 10 characters. No, it says I am going to give you all the characters that I have one by one. If you like to find the 10th characters, you can do it yourself. Okay, it is not addressable. It doesn't have a C operation. For the block devices, you have the C operation, random access, or the next one. Okay, so block devices and character devices are two categories of I/O devices. Again, these clocks, timers. Okay, we say that it doesn't fit any. I mean, it is not a block device, it's not a character device, but still, we call it an I/O device, and it's an important device. Here are some maybe outdated list of devices, I/O devices, okay, and they are sorted with respect to the data rate, starting from the keyboards, okay. 10 bytes per second should be fast enough for anybody to type, okay. You usually don't type faster than 10 bytes per second, so it should be good enough, right? I have seen people, you know those Tetris people playing Tetris on NES system? Did you see those? There is a new technique called rolling. Okay. Well, that's a very weird thing. It's just they keep their fingers on the buttons, but they keep doing this rolling motion on the bottom of the controllers, and they say that they can get more than 20 taps per second. That's why nowadays they have very, very high scores in Tetris, more than 1,000,000 points. They have to modify Tetris for. Just look this up, okay? There are hyper tappers. They are rolling people, and those hyper tappers are very, very talented. But rolling people, just regular people. But they have the. Why are you looking at me like that? I am talking about Tetris. You don't know Tetris? You don't know Tetris? I don't know what kind of people I am involved with in this class. You don't know Tetris? Okay, I give up. Back to keyboard, 10 bytes per second is enough. For the mouse, again, 10 bytes per second, because mouse, you scroll it, it gives you some very fast updates. And this is our modems. Maybe you never heard of them. 56K modems. They are used for communication over the phone lines. They are very, very slow. But I mean, this used to be in 1990s. This used to be like blazing fast, lightning fast. Okay, scanners and digital camcorders and etc. And this one talks about USB 3.0, but you have much faster USB interfaces right now. More than gigabytes, right? Tens of gigabytes. So this used to be very high-end SCSI interface, and very high-end drives, hard disk drives are connected to your system using the SCSI and etc. Okay, so these are some examples from the book. In fact, if you like to go to the more updated version of this list, just click on this one, or go to the Wikipedia and say that list of interface bitrates. Okay, we have already looked at this one. I showed you. I think I have shown you this many times, starting from maybe the first day of your class. I have shown you this maybe, and usually our simple picture is this. Okay. We have our CPU, we have our memory, and CPU actually sends virtualized, okay, CPU produces virtualized addresses. Those virtualized addresses are translated to real physical addresses so that the memory can understand them. We know that much. For the rest of the system, everybody is connected to the system bus by a controller. All the I/O devices are connected to the system bus by a controller. Controller is an electronic device. Okay, it's an electronic device. It is responsible for establishing the communication between this device and the system bus. Okay, that's why it is very, very specialized for this device. This one is very, very specialized for this device, and etc. And for the system to communicate with these controllers, okay, I need to read the next character from this keyboard. This keyboard controller is responsible for getting the pressed key and putting the code of that key in a special register inside this controller. Say that this controller in this special register says that F2BA. It puts this number inside this register, and when I read this register from the CPU, I know that somebody is doing something with the keyboard, and that would be the red keyboard character. It is the same thing. Of course, for the keyboard, you don't need much space. Maybe there is a buffer. There is a buffer of, let's say, size 200. Okay. Even if I don't read those numbers, they are kept in there. Okay. So my keyboard has a buffer of 200 characters, can hold it. If I don't read them, okay, they will be kept in there. When I read them, okay, they are gone now. I can put more characters in them. Okay. So for the keyboard, you don't need much memory inside this controller. But for the hard disk controller, okay, sometimes you need gigabytes of cache space. Okay. Sometimes gigabytes of cache space between your hard disk and system. So there is a very large buffer in there. As I said, hard disk controllers are usually very complicated. They are computers themselves, as I said before. They are computers themselves. Okay, so that's how the communication happens. You just read these special registers, or you just write to these special buffers to communicate with the device itself. Okay, to communicate with the device itself. That's the picture. Okay, the more realistic picture is this. Actually, I took this from, I don't know where. I think I took this from Wikipedia, I guess. Yeah, it is from Wikipedia. Maybe I took this 2 years ago, maybe last year, I don't remember. Usually this is the more realistic case of a CPU is here, okay? We don't have a single bus, we have many buses, okay? There is a clock generator. This clock generator is responsible for providing the clock signal to the system. We know that, okay, our CPUs operate at FE gigahertz of frequencies. You know that this clock generator is responsible for that, and the CPU is connected to this big structure. This is called, okay, this is our main bus, North Bridge and South Bridge, and North Bridge is the faster part of the main bus. Our memory, which has to be very, very fast, which has to be very, very efficiently connected to the CPU, is connected to this North Bridge part. Also, nowadays, we need to communicate with the graphics card in a very fast way. Why? Because we need to produce maybe 200 frames per second of video data, and that data is produced by the CPU sometimes, or nowadays, as I said before, we have GPUs, graphical processing units, and they are as powerful as our CPUs, and they are responsible for producing this graphics data. Or for many people, we use GPUs to do some machine learning training algorithms, or calculations of the, or maybe the runtime calculations of these deep learning based stuff. They are done on the graphics cards, GPUs, and the CPU and the GPU has to communicate in a very, very fast manner. I need to transfer lots of data between the GPU and the system main memory, and sometimes, and most of the time nowadays, you have more than the system memory amount on your GPU card. Seeing 8 gigabytes of memory on your GPU card is not an uncommon thing. Okay, so this part of the system has to be fast, the North Bridge. South Bridge is kind of connected to the North Bridge with a slower bus, South Bridge. All the other add-on devices are connected to this PCI bus. These are the PCI slots. If you have a new device to add to your system, your controller is added to these slots, and all the other stuff are connected to your South Bridge. For example, your USB devices are added here. Okay, your hard disk drives, okay, SSD drives, your Ethernet connection, your audio stuff are connected to this part of the bus. I mean, what they did, I mean, USB is fast, we know that, but it doesn't have to be as fast as these memory communication or the GPU card communication. And this is just a logical diagram, and this is the physical thing actually. This is the CPU, okay? This part is the North page. As you see, I have a very large sink on it. It gets hot, okay? Its sink is larger than the CPU's, okay? It gets hot, it's a very, very busy thing, okay? It's a very, very busy thing, and South bridge is here. So all the other stuff, for example, our SATA connectors, our hard disk stuff, USBs, and where is my PCI card? See, these are the PCI slots, and the things that are around here, see, are around this part of the board. Okay, and our PCI Express or the graphics card are just very nearby to this North bridge here, right? Good. Oh no, maybe I should draw this blue like that, right? So these are all connected to the South bridge. Anyway, this is not a course about hardware, but I mean, the picture is not as simple as this. The picture is like this, a complicated picture, and as an operating system expert or operating system student, it helps to know what's going on your main board. Good. So let me continue on this. Remember this structure. If you need to communicate with your keyboard, you need to read from this register, or you need to write to that register, okay, so that you are communicating with the device. But how do I write to this register or read from the register? There are two ways of it. Maybe you know about this from your hardware courses, okay. The first one is memory mapped I/O, okay. So each controller, as I said, has a few registers, or sometimes many registers that are used for communicating, okay. I need to write to those registers, and I read from registers. And let's see, why did I say, okay, let's ignore this part first, okay. I need to change that one. The first one is I/O port space, okay. The first way of communicating with this, there are special instructions on your instruction set for some CPUs. It says that I am going to read this port number 375 to this register, okay. So for the system, the register, the port number 375 is this one. When you issue this command to the CPU uses the system bus to go to this I/O port and read that value to the register number 5, for example. So that's how you read your controller registers to your CPU registers. Once you have that number in your register, then you can do anything you want, okay. This technique is called I/O port reading, and that space that you are reading is the I/O port space. Each control register is assigned an I/O port number, either it's an 8-bit or 16-bit integer, okay. And as an operating system designer and developer, you know the port numbers of each of your registers, okay. If I am writing the device driver for that, for example, keyboard, I know all those port numbers, and if I like to write to get something from the keyboard, then I just read it, okay. So I have special instruction for reading and writing with the I/O devices, in and out, special instructions, okay. This method is called I/O port space instructions, Okay, this is one way of doing it. The other way of doing it is that some CPU designers, they say that I don't want to make a new instruction set for communicating with the I/O devices. So what are you gonna do? I will assign. Okay, this is my address 000, and this is my top address FFF2. From this FFF2 on, let's say FFF3 will be assigned to keyboard register. Okay, keyboard register. FFF4 is going to be, for example, the mouse register, etc. So using your regular memory access instructions, if you read this address, in fact you are not reading your memory, but you are reading your I/O registers, and this is called memory mapped I/O. Okay, each control register is assigned a unique memory address, and that's actually not a memory address. That address is assigned to the control register. Whenever you use your regular load this address to my register the instruction, that's what happens. You end up reading whatever that control is giving you, and if you write to that location, then you are communicating, you are sending some data to your controller. Okay, this is called memory mapped I/O, and if I like to show you this in two different ways, okay, this is the I/O ports. This is a different address space than the memory. So for the memory, you use your regular instructions: load data, write data, etc. Okay, load and store instructions. For this one, in and out instructions. But for some CPUs it is this way. For the other CPUs it is this way. There are no special in-out instructions, but your regular memory access instructions, you are using them. One address space. Or for some CPUs they implement both. They say that you can do both. Intel architectures are usually like this. Both special instructions are available. You can do the I/O port space. Also, you can do memory mapped I/O. Okay, you can do memory mapped I/O. Two of them are available. Okay, so this is how you communicate with the I/O devices. Well, you might think that, well, that's good enough. This is how I communicate with them. But again, this is just the basics of it. On top of it, we are going to do many things. We are going to see details of those hardware after a while. Okay, so which one is better? Of course, again, the answer is it depends. For the memory mapped I/O, you don't need any special I/O instructions, so your CPU is simpler. Simpler means that if your CPU is simpler, that means that you can have more cache space, you can have more registers instead of implementing these special I/O instructions. That's good. Special instructions are not needed for the I/O space. But the thing is this: with the memory mapped I/O, this part of memory is not cacheable, right? What happens? Can you think about it? If I try to cache this part of the memory, that would be a very dangerous thing, right? I can cache this part. This part is cacheable. Put them in the cache so that I can access it very fast way. But if you cache this part of the memory, then what happens? Keyboard says that I am going to give you some number, but instead of reading this exact address, I am reading it from the cache, and I keep reading the old value. That's not a good thing. So this part should not be cacheable. So it kind of makes it more complicated to. It kind of makes it more complicated to manage the cache operations. That's one thing. It is more complicated. The other thing is this. As this picture implies, I have a separate connection between these two units, right? They say there is a memory bus. CPU and memory communicate much faster than this main bus allows. Okay, so if CPU and memory is communicating this way, when I say store the register number 1 to this address F5, which is the address of the keyboard, right? If I do this, how does the system know that the content of R1 doesn't go to the memory but the keyboard? Somebody has to make somebody has to make this decision. This data will not go through this bus, but it has to go through this bus, right?
MMU, so
What?
hocam MMU.
So somebody has to make that decision, right? So since I am using regular instructions, somebody has to make that decision, so that makes my CPU more complicated. Okay, that makes that decision more complicated. That's one of the disadvantages of memory mapped I/O. So okay, those are the disadvantages. Caching and trouble with having separate bus. Advantages, of course, every instruction that can be reference memory very conveniently. I can use any of them. Writing code is easy. No special protection mechanism is needed to keep the user from performing I/O, because I can lock that part, saying that this part is only reachable by the drivers, etc. Good. Okay, so yeah, this is this picture. Good. So now we know how to communicate with the devices, I/O devices, their controllers. We can continue with the rest of the other devices, but it looks like I am out of time now. I will stop at this point and I will continue on Monday. Okay? I'll see you on Monday.